can also help to reduce the heat dissipation. I mean, you don't lose so much heat if you tune the get to absorb the high energy photons.
Yeah. The point is that you should be able to gather the near area, the infrared, because heat is mainly comes from the infrared. Okay. But of course you can filter all the UV and visible photons. You can filter them and use them to produce electricity. So of course, that's why people are thinking of photovoltaic facades of buildings.
Thank you very much for your presentation. My question is, do you carry out the effect of solar radiation or hot temperature on the tiles? Because now in Africa we have a lot of green in cell. It is not adapted on our climate.
Yes, I understand your point, and I have to say that this is one of the points where the technology needs to improve, because stability at high temperature is still, lagging behind. So there is need for a lot of field testing and exploration of new concepts to make the technology really effective for our climates. Nowadays, as I mentioned in one of the responses, the technology is mainly suited for, let's say, Northern European climates, like Switzerland, Germany, France, Poland, but we have to make it work also at higher latitudes, lower latitudes. Yes, that's a good point. Thank you.
So let's thank the speaker.
Thank you. That's very nice.
We take a picture.
Yes, thank you. So nice. Thank you so much. Thank you. Really appreciate it. And then please send me a picture. A copy of the pictures. Thank you. So please like there. Nice. We thank for the professor for this very interesting talk. So we now continue with session 5A. Dr. Seripratio is here. Yeah, you are the chairman, yeah? Yes. So, okay, maybe I can present. You are chair, can you chair? You can go later. You can share this session, and at the end, your presentation is in this. At the end, you can present. So, for each talk. So you can organize. Yes. So please. And you can have this. For this session, we have Anna Goel. After
Serinjau, me. After OC, Karapisi, it will be clear.
I think this is not your session. This one.
Yeah, this one.
First,
So you can start.
Afternoon everyone, I am Anubhav Goyal. I am working as a postdoc researcher at Erasmus University, Rotterdam, Netherlands. And I'll be talking about analysis of photovoltaic thermal collector system which has a composite based. It's a part of a big consortium project which is known as COM2HEAT, which is simply a short form for composite for heating, and in which we are trying to replace the usage of steel through the different composite. We are trying to aim towards the bio-based composite, but let's see what happens at the end. The project is somewhere in the middle at the moment, and we at Erasmus University are responsible for a specific work package that involves the numerical modeling of various subsystems that I'll be showing, and not just the numerical modeling, also the validation with the experimental data, then sensitivity analysis, those kind of things. And today I'll be talking about one of the subsystems which is involved, which is the photovoltaic thermal system. As you can see here, it's a whole schematic showing the district heating system. It's gonna be a prototype kind of a project. So it involves a geothermal loop and a solar loop, as well as it involves heat storage and all possibilities that needs to be tested before it is scaled up. So for this particular subsystem that I am going to talk about, this is also a place where it will be tested, showing the various options for testing it. But this is a facility which is already available for geothermal loop, but we are not part of that. We will be looking after the solar loop, so I will be talking more about that. But before moving to PVT, as I have mentioned, that this project majorly concentrates or aims towards replacing the whatever subsystem it can replace with via the composites instead of steel or any other metal. So why we're trying to do that? Because the composites are resistant to corrosion or precipitation, which can increase the lifespan also in terms of transportation because it's lighter. So it can have a positive impact in terms of ecological benefits as well. Also, it is already in use for industry. Also, in terms of district heating, there are pipes made of composite which are already in use, but a whole integrated system is not at the moment there. So that was the aim of the project, and the PVT system that I'll be talking about is like in the talk I already mentioned about the PV, that is photovoltaics, and you also raised the question that it gets heat up and there is a lot of heat. So this is a system which can absorb that heat, because there is this PV panel. Most of the panels are somewhere in the efficiency of 20%, that they are able to convert the solar radiations to electrical energy, and with the specific ones like mentioned in the previous talk, it can reach to 27 or even to 30%, but on an average it's somewhere around 20%. And there is a lot of solar radiation which is available, and even the panels get heat up and atmosphere is heated as well, so you can utilize that heat, or that particular heat can be transferred for a water heating at a localized level, or it can be sent for a district heating as well. So, but before moving to the main part of modeling, I just want to talk about the kind of PVT system that are generally available, or some looks like something which is shown here, that you can see here, which consists of a PV panel, then there is an absorber plate, then tubes, and there is insulation. So it's more like an encapsulated system which utilizes the heat coming from the solar radiation or the panel that gets heat up, and that heat is only absorbed by the absorber behind the panel. But the kind of panel that we are utilizing in this particular project is a bit different. I would say it's more customized to the needs of the Netherlands. And here, as you can see, there is a PV panel, and right behind it is an absorber or simply a heat exchanger. It could be more clear from here. As you can see in this first figure, it's simply a heat exchanger, and over it, it's a PV panel. So what it does, it's not a completely insulated kind of system or encapsulated kind of system. So what happens, as you can see here, it utilizes the heat not just from the panel, but also from the ambient air. As you can see here in the slide, this is a picture which is provided by a company called ASCOM, which is also a part of this consortium working with us. So here you can see the heat that is received by the heat exchanger behind the panel. It's 20% from the panel, which is heated up, and also from the ambient air, which increases the overall efficiency. If I say the normal panels that I've shown earlier, they produce somewhere around 300 kilowatt hour per meter square over the year, but this panel has shown somewhere around almost like 500 to 600, so kind of doubling up the heat. So what we did, as I mentioned, this project is it's somewhere in the middle. So it's at the moment, it's the company called Kato is responsible for producing the composite-based heat exchanger, which involves these copper tubes and aluminum fins. But we are responsible for mathematical modeling, so we have already developed a mathematical model for this PVT system. But at the moment, it's for the usual PVT system, which involves the copper and steel pipes. I wanted to show the mathematical equations and correlations as well, as my colleague suggested you are presenting post-lunch, so don't bore people with the heat transfer equation. Better to keep it short and generalized. So, but if anyone is interested, I'm open to that, and you can ask me in detail if you want to. But here I just wanted to show the results for that. These results are the test results for this particular panel that has been tested for various various wind speed and mass flow rate. And as you can see, here, as you can see, the efficiency predictions from the experimental data and the proposed model are quite within line or within the errors of somewhere around 5 to 10%, and it also follows the fluctuations in the experimental data. So it could be said that model is good enough, but at the moment we don't have the data in terms of properties of a composite so that we can test it. But let's see what happens in the future once we have the data in terms of composite results. So in terms of conclusions, I've covered most of the points already. That is, what are the benefits of using composite in district heating system, how it will be beneficial in terms of economics or in terms of ecological aspect. In terms of mathematical model, the model is quite accurate and following within the experimental uncertainty. But one thing to mention, as I mentioned it as a note, that it's not possible to completely replace all the components of district heating system with the composite. But we have already got the heat exchanger made out of composite. I cannot disclose the materials because it's in the patent phase. And in terms of PVT system, there is a struggle. It was to be part of this presentation, but it's delayed, so it's not here. But still, if anyone is interested in this topic or find it interesting enough, or even in the future if you want to know more about it, once we have that data, so I'll be happy to share that with you. Thank you so much.
Thank you for your presentation. If you have a question. Questions? So actually, what do you expect about the financial? When we found this kind of system in the future, for instance, maybe 5 or in 6
year time, it can compensate.
Yeah, it can compensate.
But with this one, is it the same or, I mean, when we buy it and then how can we attach it?
Like a life cycle assessment.
Yeah.
Well, it's at the moment it's difficult to say the payback period, but yeah, I mean earlier it wasn't a part of our work package, but you have, as you mentioned, they want us to do the life cycle assessment as well, so we can do the payback period. But as I've mentioned, there's still, especially for the PVD system, there is still struggling with the composite metal because they want to do it with a bio-based composite. I mean, there are composite available like PP or PAT, through which they can easily make this, but that does not provide good thermal conductivity as well. They have tried it with different fillers as well, like carbon nanotubes and oxide, all these things. But still, it's not that good for environment because made from the base matrix is PP or PAT. So they want to do it with a bio-based composite or at least the fillers instead of a carbon fillers. The fillers are at least derived from some sort of bio-based material. So at the moment it's difficult to say, but yeah, this is one of the part that will also be analyzed.
In your system, you use water like
The heat transfer.
heat transfer.
Yeah, I mean these results are for water, but this system, other heat transfer fluids can also be used. In general, like PVD system usually use water or glycol.
Question?
I think no.
Thank you very much. I think it is me.
Yeah, at the end of this session.
Okay. You have galaxy.
Next
Gonzalez.
Is the one that
Gonzalez. We know.
I don't know where is the presentation.
I will be here.
Sorry.
Right. Sorry for the delay. Well, my name is Isier. I'm coming from Ternalia. This is a research company. And I will present this work. A
a framework for optimal energy vector generation, responsive distribution through metallurgic perspective. Well, this is the index. Firstly, brief introduction. Second, we discuss the problem statement. Then show the approach of the metallurgic optimization. Then say the key of the implementation. And finally, we say the conclusion and future work. Well, this is introduction. Well, this is a project that is funded by European Union, and I need to mention this because we done this work by the European. We are in the project.
Before.
This is
We focused on producing.
a video from the project, but I skip because here is more focused. In the project there are 4 consuls. One consul is from Turkey, and the consul is from Basque, the north of Spain. The third consul is from Netherlands, and the last one is from Germany. The each consortium work together to find synergies in energy, because this project is focused on enterprise that are energy intensive. There are energy intensive industries industries that require a lot of energy to do the process. So find synergies in that industry is the objective of this project. We are working in the Basque Hub, is in the north of Spain, and we are collaboration with this company in the left. And we planning certain synergies because we are focused in oxy-combustion to use oxygen and hydrogen, carbon capture to produce methane, and carbonization. Well, deepening the work we are done in this article. Here we have the challenges because the work we are working is to deal with decision support system, because we have energy intensive industries, but we have to plan how to collaborate to optimize the energy between them. So we create a complex model that is georeferenced because it's taking into account where it is located and where is production. We can deal in the problem statement. It's more clear the approach. The problem statement is based in 3 pillars. Well, the energy node with the locations. We are the scenario. We define certain location. We defined energy vector. I mean, for example, the energy, the electricity, the feedstocks, we need to the process, and the process we are in the scenario. So these are the 3 pillars. With the energy node, we define which node we are taking in consideration. For each node, we define which are located. For example, in here, an example, we are in Spain. We are in 3 capitals, for example. in free nodes. But the idea is a very complex scenario, not only to take account free nodes. With the nodes, firstly, we calculate the distance between the nodes in two ways, geodesic and on-road. I mean, because we thinking geodesic approach because it's connected, for example, with a pipeline or something like that. You don't take into account the road or the terrain. And the other approach is on road. So we complete this table with this approach. Also, we consider the energy vectors. For example, the clock electricity, what here we have in the table an example, which energy vector we consider, the units, and it's important to remark the delta unit, because in the approach, delta unit is the minimum, the smallest unit to calculate the output. Well, and finally, the final pillar is the energy process. In this example, we consider two approaches to energy process, water electricity and steam methane forming. And in this table, we characterize the parameters of the problem statement, which is maximum and minimum generation, the monetary cost, that is an approximation that the liberation or cost of energy of this technology, and which are the proportional consumption or generation of this project. Well, this is for formal modeling, how to model each processing, but we said here that there are two variables, S1 and S2, that are decision variables in this model to define in what quantity this process is produced certain energy. And also with these variables, we define the monetary cost of the production of this process. Well, for the transport model, we define a graph. How to define the graph? With the latitude and longitude of the nodes and the distance with geodesic and on road. This graph is how to model the transport system, the transport model. And we resolve this sub-problem with algorithm minimum spanning tree. This is a deterministic algorithm. And also we are exploring multiple spanning tree that is not a deterministic algorithm. So we are this is under research now. To solve this problem, where produced and how and in which quantity is resolved with metallistic algorithm. And how to these are definition is here. The objective is to minimize the monetary cost, and is divided in generator and transport. So it's clear. And this function cost is subject to certain constraints. For example, the first constraint is defined by the process. Each process has a maximum and minimum limit of generation. The second constraint is related to the total energy of the scenario. The third constraint is the limitation, which in certain nodes, as the user of the scenario, we define a limitation which not produce at certain, for example, certain energy vector is defined a maximum. And the last one is in certain nodes, certain processes are not can be deployed. Well, in here how to model the problem and how to transform these variables into the metaheuristic algorithm are defined here. We use a integral approach, because we define that the delta that mentioned before is the minimum energy that is considered. Well, when we implemented this, we found certain troubles. Well, because metaheuristic is to try to optimize something that is not you are not very sure how to resolve. In metaheuristic is one key is to the first generation of the metaheuristic is very key to resolve. So here we miss with integrated programming to generate the first population of the metaheuristic optimization. And so we merge two approaches, metaheuristic and linear programming, to find an optimal solution in less time. Implementation. Well, implementation is here in Python. We use certain well-known libraries. For example, GeoPandas to reference the nodes of latitude and longitude. The graph are with using networks. The optimization algorithms are using with the library PayMo. And well, and finally there are generalistic libraries like Plotly, Pandas, NumPy. Well, conclusion, this paper focuses on framework to optimize the energy consumption distribution, based on three pillars: nodes, vectors, vectors, and process. The part of the transportation, we have two alternatives, geodesic and on-road. And the objective to minimize the total money cost, generation of distribution, and to solve this, we use metaheuristic linear programming. Evaluation in this article, we only show the framework of how to resolve it, but for the paper, we use a real case, a real scenario, very huge, with more process, more geographic nodes, and using a invitation heuristic to attain the framework and efficiency. That's it, more or less. I think it's.
Thank you very much. Questions? Questions?
I think this is yes.
I have a question. For your implementation, you are using Python.
Yes.
Is it possible to use MATLAB?
Yes, I'm very familiar with that, but in the past we used a lot of code implemented in MATLAB, but we changed, my group, we changed it with Python because the MATLAB license is not free. We have a license, but Python I think is nowadays is more more supportive. Also, there are libraries in artificial intelligence, like PyTorch, that is, I think is very, well, MATLAB is not comparable with Python in the sense. But, well, both approaches I think are good. MATLAB or Python. Any more questions? Thank you. Thank you.
Daniel?
My name is Daniel Teso, and today I am going to present my recent project, which is how to improve IoT devices in energy efficiency using a technique which is called ECRES, Adaptive Neurofuzzy Interest System. So we have to know that those devices are changing the many sectors, such as agriculture, and thanks to those devices, now we are working more smarter, more efficient, more safe. But however, we know that they have a clear challenge, which is the battery consumption. We have to take in mind that those devices, some cases, operate in a remote areas, in which recharge or replace the battery is really difficult. And also, many of those devices uses fixed rules in which all the time appear this data with the same frequency. So they are consuming a lot of energy. So the idea is to introduce an intelligence to those devices in order to change the behavior depending on the environmental conditions. The idea is to adopt this technique, which helps us the neural networks to learn capability, and also the facility rules in order to change this behavior easily. The idea is to imagine one of those devices operating in a remote area in which they use a battery and a minimal solar panel to recharge that battery. And the device detects that the battery is really low, but however, with a light sensor, we can see that there is a lot of sound. So in order to maintain the same frequency to take that data, we reduce the frequency and we improve the rechargement of that battery. Thanks to that, we are going to improve the energy consumption. Also, we are going to reduce the maintenance because the battery will have a more period of time work, and in the end, we are being more efficient with the environment thanks to this lower maintenance and human intervention. So, to make this possible, this sensor, this device has different sensors. The first one, obviously, how many battery we have. The other one, the environmental condition with the temperature. And also, we have a light sensor to check how many sound we have in that moment. And here you have the data that we collect to train the artificial neural network. More or less, we have 10 days data acquisition, and here is a piece of 3 days. And also, you can check that there is a humidity from the atmosphere, but for this experiment, we don't use. If we focus in temperature, for example, we can check this period of this data. There is a sunny, because the temperature goes from 7 degrees to 25 degrees. Also, if we check the luminosity, there is a lot of sun, but the battery dries out. It declines gradually from this 3.7 volts, more or less to 3.4 volts. So, also we have to know which device we have in this IoT device. In this case, we use an ESP32 microcontroller because it has a function to disconnect the peripheral devices such as Wi-Fi, Bluetooth, and thanks to that we can reduce this energy consumption. And also we have to take in mind that those devices hasn't got enough power to train artificial neural networks, so we need another computer to train this model. And then after train, we transfer the fuzzy logic rule, the fuzzy logic rules to the device using C code. Here you have the more or less the trained Danfish rules, in which you can see, depending on the variable, which members function we have. And if we put in a comparison between the real device without Anfish model and compared with introducing this Anfish model in the same device, we can check that there is a difference. And also it's important to know that this device has a minimum intelligence because it has some deeper sleep range difference, goes from 5 minutes to 120 minutes, deeper sleep cycles, but there is not enough optimization for those devices. And thanks to Anfish model, we can say that operate smoothly. And also if we can check from 100 to 200 sample time, we avoid some unnecessary wake-ups. And in a simulation we can check that we can improve that battery consumption around 20% thanks to those avoiding wake-ups time. So, this, as a conclusion of this experiment, we can check introducing an artificial neural network in those devices. We can improve the battery consumption. Also, we are going to reduce the battery maintenance, and in the end, we are more eco-friendly with those devices. Also, we know that 10 days data sheet is not enough to conclude this experiment, and now we are taking more data in order to fine-tune of this artificial neural network. So, thank you so much, and if you have any questions,
It is very interesting work. It is very interesting work. I have to get it out. In the Anfish system, there are three variables. Input
Yes.
variables, three.
yes, today we are using 3 variables, which is the temperature, in order to check how many degrees we have, because in Spain on sunny days we have 30 degrees in some cases, and if we recharge that battery with a high power, we maybe reduce the battery life. So thanks to the temperature control, we can check it. And also with the luminosity, we can see how many sun we have in order to change these sleep cycles. And the other variable in this case is how to check the battery condition of that cost.
Okay. And the output of the system, it has got a range between 0 and 1, or?
The facility has 0 to 1 output, but we transform into minutes. And in that case, the device goes from 5 minutes, which is the lowest deepest sleep cycle, to highest one, which is 120 minutes.
The variable
Yes. In the end, we are changing the deepest sleep cycles to reduce that data frequency.
Okay. Very interesting.
Okay. Michel?
technique, I mean, your approach with the traditional approach, have you made get some logs, data logs, comparing these two techniques? I mean, this technique with a common use of battery, right?
With the comparison that we make, it's the real device with this improvement. We don't have enough time to check another systems.
Okay, and the other question was a comment, the training of for artificial intelligence. You wrote that you did outside, because otherwise it's very energy consuming. So
And also the microcontroller has enough power. Because,
yeah, of course. So I mean, if you take into account also of that consumption, so did you compare this?
In a global shape.
Yeah, exactly. With a common.
We didn't do that. It is a good reflection to take in mind and to check how many energy we are reducing making this. It will be a good idea to take in mind for next.
Just to compare, I mean, the overall power consumption, no, from the beginning.
And the real, no?
Yeah, the real
reducing.
one. Also for training, take into account also training of the AI.
Okay.
Okay, thank you.
And I recognize from this picture that you have also shaded cells there. Yeah, shaded cells on the field. And partial shading methodology also should be applied here to get the correct current voltage according to the illumination, because illumination is one of the important parameters in the graph. So they should also take into account
Shades.
partial shading effect here. I mean, if you use in this
Yeah, in this
garden,
Yes.
it's just a recognition.
It is to make a point.
Science is serious. Science is serious.
Thank you.
Okay. Good. Okay. Okay, so I think last speaker in this session.
Yes.
So, Serena Theo will talk about the experimental and numerical study of a double slope solar scheme for rainwater or seawater treatment in remote area.
Thank you very much. I am Serine Diaw, associate professor at Associate University of Ziguinchor in Senegal. My topic is experimental numerical study of double solar scheme for rainwater or seawater treatment in remote area. I follow this summary, introduction, context and objective, material and methods. At first, theoretical system description, experimental system description, result and discussion. At first, numerical result, follow up experimental result, at the end, conclusion and perspective. Access to fresh water in remote rural area is a real challenge. The critical need for clean and accessible water is in fresh water plays a vital role in not only in maintaining human health, environmental stability, and to preserve our planet, but also is a key element in overall development. To meet this challenge, the implementation of water treatment technology must be encouraged. solid water source like groundwater or seawater can be processed to provide fresh water using different technology. Different desalination method has been used to address the growing demand for fresh water like melt effect distillation, MSF, melt estage distillation, vapor compression, or reverse osmosis. Solar distillation system is a promising technology which collects solar energy to produce fresh water by the process of evaporation and condensation in the basin. Our objective is to provide large quantity of drinking water at low cost and in an environmentally friendly manner. Solar thermal technology is well suited for water desalination. It does not require enough maintenance, with a long operation lifespan. Solar distillation system is a promising technology, especially in areas where solar radiation is abundant. Solar thermal energy is in abundance in a country like Senegal, where direct solar radiation is an average of 90-15 kilowatt-hour per square meter per year, with more than 3,000 hours of sunshine. Solar distillers are therefore well suited, especially in simple double solar steel. In this paper, an experimental and numerical study using safety of solar steel will be carried out. We have the three-dimensional double solar steel with the component, the glass cover, the insulation, absorber plate, green water or seawater inlet, and also the distilled water outlet. We can carry out the energy balance of this component like glass cover, basin, water in the basin, or saline water. Also, it is possible to carry out the quantity of distilled water, also to carry out the efficiency of our system. For the experimental system, it is located at the Center of Estate and Renewable Energy at the University of Dakar. It is a dual solar steel which an area of 2.5 meter and a thickness of 0.15 meter. It is covered with transparent glass, 0.98 meter longer and 0.51 meter of wide, inclining at 16 degrees to minimize thermal loss. The wood is insulated by a black line. It has a very simple design and has the advantage of being easy to build and maintain. For the result, numerical result at first, in this part, we use ANSYS plans to perform our system. In order to faithfully reproduce the experimental condition, we performed a multi-phase simulation using the Perugian method. The geometry of the solar steel was designed according to the experimental using the ANSYS discovery driving tools with the following dimension: a rectangular parallel basin, inclined flat, two slope inclined at 16 degrees, lines 0.98, wide 0.51 meters. We also integrate the coordinate of the experimental site directly into ANSYS plans using the solar calculator. And we have a mass dependence analysis, and it was performed. This allows us to obtain the solar radiation parameter given in table 1. We have the directional vector of the sun, fraction of sunshine, direct normal solar radiation, diffuse solar radiation vertical surface, and diffuse solar irradiation horizontal surface. Also, we have the solar irradiation reflected from the ground. And now we have the result in figure 3, 4, and 5. In figure 3 we have the volume fraction, in figure 4% of water volume fraction, and in figure 5 we have the volume fraction water. The formation of water mist due to the cooling of the steam in contact with the ceiling lead to the appearance of a volume fraction of water at this level. A significant accumulation of this volume fraction is also observed in the recovering pipes, which confirm the correct operation of the numerical model and the adequate consideration of the evaporation condensation phenomena. Also, we have the temperature profile in figure 6 and also in figure 7. The temperature is significantly higher at the top of the roof slope. However, it gradually decreases as one approach of the recovery pipes, thus promoting condensation in this area. For the experimental result, at first we use well water, and at the second part we are using CVC water. In this part, green water was used. We carried out the performance of the system by measuring the quantity of distilled water. After several experiments, the distiller is emptied, cleaned, and the basin repaired before it was put into operation again. And we have the result in the table 2. And here we have we carried out the measurement between July and August, and the measurements are carried so that for August we noticed the low volume for August 13, 2020 to 24. This is due to poor solar irradiation. The low volume measured for the day of August 25, 2024 are due to a deposit of solid particles on the absorber due to the fact that the distiller remained for a long time without being cleaned. In figure 8 we have the volume of distilled water measuring at 9 a.m. the day after each test using green water. After doing the test, we the day before, the day after, before to do another test, we carry out the quantity of distilled water obtained. And figure 8, in figure 8, we noted a large volume of distilled green water. This is because during the night, glass cover is solid and large amount of water vapor is condensed. Now we use seawater. To be more realistic, the distiller was emptied and filled with seawater. For this method, we also measured the quantity of distilled water produced for each test. The solar irradiation and different temperatures were also measured. In order to establish the performance of our system, part of the solar steel is covered by plastic sheet as shown in figure 9. The same test was also carried out using cardboard as seen in figure 10. Similarly, we set up a solar reflector system to further increase solar irradiation in the distiller as shown in figure 11. And the result obtained for these different tests are given in figure 12, 13, 14, and 15. Four tests were carried out. For each test, we carried out the parameter has temperature inside the solar steel, temperature outside the solar steel, and seawater temperature at the end the solar irradiation. The volume of distilled water obtained when the system is covered with black plastic is 1.53 liter, as shown in table 3. This volume is very small. Also, the experimental was carried out on a cleaning sunny day. The black plastic absorbs heat, making the glass much warmer, which is not very favorable to condensation. The curve with the black plastic causes the greenhouse effect in the distiller. Also, when the solar steel is covered by carbon, the volume of distilled water obtained is 2.07 liter. The glass cover is less hot in comparison with the experiment using a black plastic cloth. The maximum of solar irradiation of this day was 1,113 kilowatt per square meter, therefore a significant solar radiation. When the sun moves, condensation occurs on both sides, but it is more significant on the uncovered part. This is due to the fact that the sun's rays cannot longer enter since this part is covered. We placed the galvanized metal flat of the solar steel, which reflects the solar radiation in the solar steel. This day was cloudy, with low solar radiation. The high temperature of seawater inside the solar steel was observed. Also, the solar steel received two solar irradiation at the same time. The solar irradiation received directly from the sun, and the irradiation reflected by the galvanized metal flat. This is the origin of this high temperature. However, the solar steel only produces 3.15 liter on this day, as shown in table 3. This is due to the fact that the water droplets formed are very large and will fall back into the distiller basin. Here we have the volume of seawater distilled the day after its test. And this figure shows that the quantity of distilled water obtained the day after its test are significant. However, this quantity of distilled water is greater when the distiller is equipped with reflector. The reflector concentrates solar irradiation on the glass cover area of the distiller. This will cause an increase of seawater temperature in the solar steel, and therefore a strong evaporation and condensation of the water. In conclusion, access to drink water is a major problem in rural and urban areas. This is often a source of illness and therefore an hindrance to development. For better condition of population, it is necessary to encourage research in the field of solar distillation. Our study shows that with a sample solar distillate, it is possible to obtain 6 liters of distilled water. In order to better control the model and increase the quantity of distilled distillate produced, a numerical analysis using CFD was carried out. As perspective, we want to conduct a chemical characterization of the distillate to determine the mineral salt content. Also to conduct a technical and economic study to determine the profitability of our system. Thank you for your attention.
Thank you very much for this interesting talk. Questions? Yes, please.
Thank you for your presentation. I have a question regarding the brine water. That how are you disposing it? You are throwing it back to sea or doing something else with that, or you are reusing it?
Right. At first, we use green water. At first, to see if our system works correctly or not.
Okay.
After this, we use seawater, seawater, because our objective is to use seawater.
I just want to ask that what are you doing with the remaining water after the evaporation condensation cycle is done? The water that remains has even more salt content. So what are you doing with that? How are you disposing that?
For green water,
Can you repeat again?
Yeah. I would ask that what are you doing with the water that remains after the condensation evaporation cycle is done? I mean, you have received some water is converted to distilled water. What happens to the rest?
He is asking to the rest of the water.
the rest of
Yes, after this.
Okay. After we can cleaning the basin and we feed a new green water or CCC water.
The final code will be salt. The final code inside the stage inside will be salt or rainwater. So inside
Inside the basin.
exactly.
Salt.
Wait, salt water. At no time we have salt water in the basin. Yes. And we cleaning the basin before carrying out another place.
It's possible to use salt into cooking or something like this.
Why not?
Yeah. Have you done some statistics on these numbers? Because you were presenting numbers with 4 digital points, and I'm wondering if there are some errors associated with the numbers that you have presented or not. So I mean, if you have some statistics on the data that you have presented.
Some statistics?
Yeah.
Now, no. I say for perspective, we try to do the economical part to have aesthetic. Because here we have 6 liters of distilled water for an area of 2.5 of distilled water.
I think he needs much more work.
Yeah, for sure.
I would have a question again. Have you thought to compare this approach to another approach, like for example, using electrolysis, the photovoltaic panels, to just distill your water or separating water from pollutant?
Okay.
So in order to compare the different approaches.
Okay. Using reverse osmosis
Yeah, reverse osmosis.
is more efficient because when you use reverse osmosis, you use compressor, and when you use compressor, you use electricity. And here, we want to use only solar thermal area.
Without using electricity.
Exactly.
But there can be also hybrid system.
Exactly.
You can also make another work on a hybrid system.
Exactly.
With Francesco's ideas. And that can be also very interesting.
To
Yes,
this
yes.
comparison.
You can combine it. Why not? Because this kind of, hybrid systems get too much interest from the yes.
It is possible, yes.
Yeah, for example, combining photovoltaics and thermal harvesting or light harvesting as you do, for example, you just exploit irradiation from solar, not in the sun, but maybe you can use also, you can produce electricity with a small solar panel and to improve the efficiency of the, the distillation.
Okay, it is possible.
Questions? No? Okay. Thank you very much. One is for your participation, so maybe you can make that. And, one other is for the,
Coffee break.
Nasıl dayanamıyoruz?